Good evening, everyone. Myself, Suresh Kannaujiya. I am from Geosciences Department. I am going to talk about advanced GNSS data processing. So, before I start this lecture, I would like to highlight something. So, why we need advanced GNSS data processing? Because we know that the application of GNSS is to get the position. Okay, latitude, longitude, height, and if you want additional parameter like time, so we can estimate this with the help of minimum 4 satellite. And if there are more number of satellites, so it constrain our this 4 parameter x, y, z and time. So we know that there are so many applications where we use this technology. Fisheries, we use in fisheries, we use in crustal deformation, we use in active fault mapping, active fault characterization, then landslide monitoring, subsidence monitoring. Then you are going for this GCP collection. You want to validate something, then and then if you want to make digital elevation model, then you need very accurate latitude, longitude, and height information, so that you can do the ortho rectification and this you can implement this data during this digital elevation model preparation. So there are so many applications of GNSS, but in some cases we need some centimeter accuracy, some millimeter accuracy. So there are different requirement of GNSS applications. So and then accuracy is also different for different application. Then precision is also different. But when we talk about monitoring, so then we talk about advanced GNSS data processing, because this monitoring we cannot get without advanced GNSS data processing. So there are so many open source software you can use it, like Gypsy is there, Gamut Globe K is there. Okay, then this license version Bernie software is there, and which you can use your data for advanced GNSS data processing, and where you can constant all this data and get the millimeter and centimeter accuracy. So I am going to talk about all these aspects, including fundamental of GNSS, followed by the your how we can model the GNSS data, then how it limits our accuracy. So what we how we can take care, because this is not something like we are downloading the data and we are getting and we are using for our application, because here it is very different. Here we have to take the instrument, we have to go to the field, we have to acquire from our side. So this is the new challenge actually when we are working in GNSS, because this processing is you can handle easily when you have acquired accurate data. So when I talk about accurate data, so when you are going to set up the station, so you have to consider so many steps, and very precisely and accurately, so that you can acquire the data very nicely manner, and then all this data can be processed by the DGPS method or by the post processing methodology. So this is the thing. So in this image you can see that this is showing the ITRF 2014 horizontal velocity field. So these are the resultant motion which has been estimated with the help of IGS data all around the earth using gamut solution. So you can see these all are representing millimeter accuracy. Some of the plates are moving in means 50 millimeter, 40 millimeter, 30 millimeter, 60 millimeter, so like that. So all this millimeter velocity is estimated with the help of advanced GNSS data processing. So this is the consciousness of this methodology to provide the very accurate information, either in sigma 1 like 67% accuracy, like sigma 2 95% accuracy, but we mostly estimate in this uh, error budget only, either sigma 1 or sigma 2. Sigma 3 is very impractical, so we mostly try to get our solution between this error range. So you know all this constellation, and all this has been covered by our previous faculty member. So GNSS is the constellation of mainly six satellites: your Galileo, GLONASS, Beidou, GPS, QZSS, and NAVIC, our INSS. So in which two are regional, and rest are global. So here is the specification of all the your this constellation. So you can see all are basically orbiting in MOU, except few of the satellites of Beidou, QZSS, and NAVIC. They are uh, basically orbiting from either GSO, geosynchronous orbit, or GEO, geostationary orbit, because due to the different objective and limited number of satellite, and they are mostly focusing on the regional region. So this is how we basically set up the station. So you can see here this continuously operating reference station on this left side, and on the right side you can see the campaign station. So this is the benchmark. So you can see that benchmark. This is how you create the benchmark, and then you go and acquire the data on some reference point, and after getting minimum 3 point where we believe that it will get r square approximate near approach to 1, then we can say that this data is reliable for monitoring purpose. So when r square is reaching to 1, so then this campaign data, I'm mainly talking about the campaign data. So here it is involved very means very good care when we are going to set up the campaign station, because here we have to do the centering and labeling, then only this setup can be completed. And after the completion, you have to make sure that because this is going to acquire for an hour or for a day, so when it is acquiring the data, it we believe that it will not subside, it will basically study at that location at that point for an hour or for a day. And this continuous has a very unique this constellation your setup, because this is acquiring the data 24 into 7 into 365 days continuously for 10 years or 15 years or so. So the objective is very different. It is called base station. But when we talk with respect to IGS, so this is rover. So but and when we talk about campaign station, so we can use this when you can we can use this as a base station to process our campaign data. So when we are going for this static monitoring, our kinematic monitoring, so there are different means purpose of using this base and campaign setup for kinematic monitoring and as well as static monitoring. So this is another this base station. So like that we have approximately 15 station, and ISRO is having approximately 22-23 station in Himalaya, in northwest Himalaya. So this is the this antenna. So this is called chokering antenna, Dawn Morgling chokering antenna, and this is the very high grade GNSS receiver. So this is the campaign setup. So this is how it look like. So the purpose of chokering antenna to reduce the multipath, because we know that when this GPS satellite, our GNSS satellite, it's transmitting the electromagnetic wave. Basically, it is coming in right-handed polarization. It is having right-handed circular polarization. So and here it is intended to receive those polarization only. If there is a left-handed circularly polarized polarization is there, so it will not receive. So purpose of this chokering antenna, if signal is coming from low horizon or it is having huge multipath, so it can be reflected back and this polarization can be converted with the help of this technology. And this is the campaign this antenna as well as receiver, and this is your net and receiver. So here the outline is, now I will mainly focus on this theoretical part and the case study part, and these are the outline. So we all know that this GPS presently the constellation is carrying three frequency, L1, L2 and L5. But here L1 and L2 is important for us, because why we use two frequency, because there are so many errors which is associated with the data. So if you want to eliminate all those error from the data, so you need minimum two frequency. So this is the frequency where the wavelength is 19 centimeter, and L2 this frequency is this, and wavelength is 24 centimeter, and this is carrying by this fundamental frequency. So you can see this is the carrier for this coarse versus acquisition signal, and P code. P code is basically the protected or precise code, and we can say that this can be in the form of carrier wave also. So it is basically carrying at this frequency, okay, and it is coming on the surface, and then it is detected by the ground antenna, our users. So navigation message, it is basically carrying the system time, broadcast orbit, system clock, correction, almanac, ionospheric information, okay, for both L1 and L2. Then this is the basically square wave. This is how it look like, and this is the carrier wave. So you can see that you can now imagine the difference between this is square wave and carrier wave. So this is also called phase wave, but this is not having any phase information. This is ranging between 0 and 1, but here each second there is information. So that's why this carrier wave is very important when we are going for this monitoring purpose. So these are the models. So this is for the pseudo range measurement model, and this is the phase measurement model. So here we are basically interested in length measurement. Okay, so there are so many errors associated with their data. So once we eliminate, so initially we get the pseudo range, and then after the correction, after the implementation of the error, we get the true range between the satellite and the ground antenna. So these are the equations we want to basically use it, and for the estimation of latitude, longitude, height and time. And this latitude, longitude, basically we are taking the reference of equator and prime meridian, and height, basically we are taking the reference datum is your ellipsoidal model of the earth, and time we are getting the time from the GPS satellite data. So when we want to estimate this different parameter associated with this navigation satellite, so we use this Keplerian method. So Keplerian method basically is it has the ability to provide the position of the satellite at an instant of the signal transmission, and which is very important, because we know that due to the gravitational pulling, due to the solar radiation pressure and other phenomena, other atmospheric phenomena, so the intended orbit is not possible. This mathematical orbit is not possible. So there is a perturbation in the orbit. So we need this orbit data, and we need the position of the satellite, so that we can model it, and we can correct the orbit of the satellite, so that we can estimate the precise distance between these two satellites and your ground antenna. And how this is possible? You know the Kepler's 3 law. I am not going to talk about here because I have a limited time. So you know this 3 law: orbital ellipse, law of equal areas, and orbits with equal periods. So with this help of this 3 law, we are able to know this 6 parameters: semi-major axis, eccentricity, inclination, longitude, argument of perigee, true anomaly. So what it defines actually, what it gives, what information it provides, all these parameters. So with the help of these 2 parameters, we can get the information about the size and shape of the orbit, and with this three parameter we can get the orbital plane in the apparent system, and this MA is basically mean anomaly position in the plane. So once we get this information, then we have to implement all this into the fundamental formula. So before going to this, we have to understand what is carrier phase. Okay, so carrier phase basically is the angle of rotation. So if there is a 360, if there is a circle, so this complete circle makes a 360-degree angle. So suppose for an instant, this point is on some part of the circle. So that circle is basically defining that somewhere on the sinusoidal wave, actually somewhere on the sinusoidal wave. So I will explain you in the subsequent slide. So first you have to understand what is phase. So phase is the angle of rotation. Okay, so in a unit cycle for GNSS analysis, and phase can be thought of a measure of time. Okay, so how it can be a measure of time? Because with the help of this phenomena we can get the precise time, because there is a variation in subsecond, in second. So this information is very beneficial for getting the precise time, that when this your satellite signal hitting the antenna, and this replica signal which is creating into the receiver, it is correlating to each other, means cross correlation is going on between this satellite signal and replica signal which is created by the receiver. So then there is a time delay. So this time delay we are able to know because of this phase observation. So TT is the time according to our your clock at time t, and phi naught is equal to phi, this phi subscript naught, phi naught is so that the clock reads 0 at time 0. So when we talk about the angular speed, so this is the formula, equivalent formula. And when we talk about this ideal clock, so this is the formula for the ideal clock, f naught t plus phi naught. So if there is ideal this ideal time, then how would be this equation? So when you implement this formula into this equation, then you will get ideal time, and where k is the k is equivalent to 1 upon f naught, and where f naught is the nominal frequency of the oscillator. And when we keep this k naught into this equation, so ultimately we get the time, clock time, and this is the equation. So now, how phase is related to periodic signal? Okay, so you know you must have gone through this technometry. So this is the phase, this is the sinusoidal signal, and as I was talking about the circle, and suppose for an instant this the signal is here, so it has taken time t, and it has then a naught is the basically the constant amplitude, and at is the signal. So this is the complete equation for this formula, and then you can see that a naught is the radius of the circle, at is the signal, and a naught is the amplitude. So when we want to see how it would look like for ideal this signal, so it will be like this. So when you will and you know what is the phi ideal. So once you keep this phi ideal here, so you will get the signal like, you will get the equation like this, and then you can expand this sign into this, so you will get complete this expansion of this formula. And after the formulation, so you can see that it is having the sine component and cosine component, and this complete equation is the basically the periodic signal, and which is also called phase for the precise positioning. So when as I was talking about this your satellite signal and replica signal, so when we do the cross correlation, so as just in previous slide we got this equation. So when we keep this equation and when we reformulate this, so we get the signal like, so we get the equation like this. So and you can see there is a low frequency component and high frequency component. So we want to eliminate the high frequency component and we want to keep the low frequency component. So after filtering this, RT into cross correlation GT. So we get the low frequency component, and this is the formula for. And after considering this phi bt, and this phi bt is nothing but it's basically the phase signal, which is the subtraction between the your replica signal and the your carrier signal, your satellite signal. And this is the frequency of the replica frequency and carrier your satellite frequency. And this is the carrier phase observation model. So when we implement the previous this equation for this carrier phase model generation, so we get the this is the equation, and where there is a time delay and there is a phase delay and there are some more error associated with the signal. So we want to correct all this. We want to estimate first all these parameters so that we can do the correction, and then we can estimate the precise phase. And when we get the precise phase, so we use it for estimation of the unit length, and this is the formula to estimate the unit length. And after the expansion, and this is the formula where there is a zenith delay, ionospheric delay, multipath, clock error, your satellite clock error, receiver clock error, some more error like satellite motion, phase center variation, some your this atmospheric your loading error. So all those after implementation of the error, you can estimate the unit length. And this is the formula to get the single difference sensing, and it helps us to estimate the clock bias, satellite clock bias. And this double difference sensing basically eliminate the receiver clock bias. So this is the this some signal information for different this satellite, like this is G07, this is G28, G26, G11 and G02. So you can see that this for this time period, this is carrying different information. All these satellites carrying different info and very crucial information, because this is the information which help us to determine the very precise positioning on the surface of the earth. So this is the observables, and we basically set up these equations, and we have to follow all these steps so that we can model this Rhinex data, and through these following steps, and get the your 4 parameters precisely. So this L1 phase, L2 phase. So this L1 phase basically we are getting after multiplying with F1 into range, and L2 F2 into range. Then C1 P1 pseudo range used separately to get the receiver clock offset. And then when we want to eliminate the ionosphere, so we have to make the linear combination using L1 and L2 frequency, and with some constant factor. And then when we want to eliminate this, this is in cycle and this is in meter. So you can see this. We have to use this pseudo range formula. And this double difference basically removes the clock fluctuation, remove almost all the ionosphere, but what happens, it amplifies the noise. So you want to eliminate all those error also, so you have to use this geometry combination, this formula you have to use. Then some additional this Melbourne Webinar wide lane you have to use to eliminate the pseudo range noise, and some geometry which is still there after implementation of the previous formula. So this is the formula for this MW and WL correction. So apart from this very traditional error, there are some more error actually, which is very crucial to implement into the data. So we should have this model also, like motion of the satellites. Okay, so like Earth gravity field, attraction of moon and sun, solar radiation pressure. So these two basically has some pattern, so it can model accurately with the help of some data set. But the solar radiation pressure is very dynamic, so it is not easily modeled. Motion of the earth, so you can use basically you can model this irregular rotation of the earth, lunisolar solid earth tides you can model. But this loading due to oceans, atmosphere, and your surface water and ice, it is very difficult to model because data is not available directly for modeling this all parameter. Then propagation of the signal. So this neutral atmosphere, ionosphere can be modeled because we have the data, accurate data, but this variation in the phase center of the ground and the satellite antenna is not completely modeled. And apart from that, when we are preparing for this data processing, so we need the satellite orbit. So this ephemeris data sp3, which is very accurate, which we get, there are so many this basically data provider. So and also there are some rapid orbit file, our final orbit file, okay, then quick orbit file. So there are different actually accuracy, this orbit file is available on the this website, so which we can use, and depending on your requirement you can use it and get your this data processing done. Then gamete tabulated ephemeris is also very important. So you have to get all these parameter into the gamete folder. Then motion of the earth in inertial space. So you have to basically get all this parameter, and there are, this is very important. Your Earth International Earth Rotation Services providing the rotation, this regular rotation of the Earth, and this is the nodal agency for providing this rotation data. Then propagation of the signal. So you know our this GNSS signal is propagating through ionosphere and troposphere. So ionosphere we are able to monitor, but this when we talk about, when we come to this this troposphere, so there is two component, dry component and wet component. So this dry component is mainly having pressure and temperature, and wet component is having water vapor. So water vapor is very dynamic, and it is not very accurately modeled. So we need so many data, so many different data set to model the water vapor. So this is called zenith hydrostatic delay from the pressure and zenith wet delay from the water vapor. So you can have this mapping function, which is also called VMF1 grid. Our GMT, through GMT we can get it. Then once we get this all this preparation has been done, then we apply all these steps to get the constantly loosely constant solution. So once we get the loosely constant solution, we apply this globe K to get the this fixed solution and time series as well as velocity of the station, we get it. And for this all this time series and velocity estimation, we use the Kalman filter, and which basically bring into the sequence, and it gives a very constant continuous solution of all the station's data. So what are the different these parameters which limits the GNSS accuracy? So like GNSS propagation effect, like signal scattering. So when signal scattering is taking place at antenna phase center, our multipath. Then atmospheric delay, mainly water vapor. Ionospheric effect, if there is a random ionospheric variation is there, so it is not easily modeled. Then receiver noise. So and then some unmodeled motion of the station, like monument instability. So as I was talking about the, when we set up this this campaign station, our permanent station, so we have to very carefully have the knowledge about the area, our where we are going to set up the station, that where our station will sustain there or not, because we cannot expect any motion or any movement locally at nearby our station. So if there is any motion, so we cannot model it. So that's why it comes under unmodeled motion of the station. So then loading of the crust by atmosphere and ocean and surface water. Then unmodeled motion of the satellite. Some satellites motion is very unpredictable and cannot be modeled. Then reference frame. So reference frame is nothing but it's a frame which we are using it to fix the solution, and so that we can get the this our coordinates in either in geocentric coordinate or in WGS84, our ellipsoidal model of the Earth. So when we want to get our data in this different reference data, so we need very accurate and very precise reference frame. And if there is any error in the reference frame, so our this solution will have a error association, and which cause a misinterpretation. So because sometime because we this is not in our control, so this is providing by MIT USA, our different agency, where they are using various data sets like VLBI, SLR, your Doris, then 500 plus IGS GNSS station, then some more data sets they are using, and then they are modeling all those data sets together, and then they are providing this reference frame in ITRF, International Terrestrial Reference Frame. So these are the different GPS error sources. So how satellite orbits can have a error? So satellite clocks, tropospheric refraction. So how there can be this error association? So you can go through later on because time is limited. So I have to complete. Then GPS error sources like in ionosphere refraction is also there, antenna phase center variation is there, multipart is there. I have already talked about all this thing, and it is elaborated in this text form also, so which you can go later on and you can read it through my video. And if you have any more doubt, you can contact me through email or through various channel. So if there are many errors, so you can see that how much error can be associated fundamentally. So satellite clock can have this 2m, then orbit can have 2.5. Ionospheric is the highest, it is having plus minus 5m, and tropospheric having minimum 0.5, then receiver is having 0.3, and multipath is having 1. So this ionospheric is having the tremendous error, so we have to have this correction this into our data, so that all this error can be eliminated from the data. And this is the basically the more information about this signal propagation effect. So you can see that what is multipath actually. So you know that we are intended to receive in our ground antenna the direct signal. Direct signal means which is directly coming from the your this signal satellite to the ground antenna, means it is direct into the line of sight. But what happens when signal is also means interacting in our buildings, our canopy, then it is reflecting back to the your this antenna, and then it is going toward antenna. So if the antenna is not chokering antenna, then what will happen? It will receive all those multipath also. So that's why the purpose of multipath, the purpose of chokering antenna, is to reflect back this multipath signal, so that this signal can be avoided during the recording, and we only intended to receive we maximum receive the direct signal. Because when signal is coming from low horizon, means from low elevation angle, because you know that we know the position of the satellite through two parameter, elevation angle and azimuth angle. So this elevation angle basically we calculate from the north, and azimuth angle elevation angle we calculate from the base of the antenna, and azimuth angle we calculate from the north of the this our in this earth. So when we calculate this, so we get the position of the satellite. So when this signal is satellite is present between 0 elevation angle to 10-degree elevation angle, so then it has to travel the maximum distance through the ionosphere, as well as it has to travel through the various canopy. So then what happened? Signal loss take place. So and it is called cycle sleep. So due to this cycle sleep, what happens? Your signal loss take place. So it can be restored and there is a module for that. So in gamete module you can restore all those cycle sleep, and then you can so that you can process this data efficiently. And sometime what we do, we basically restrict this low elevation degree satellite data, because when we are going to acquire the data, so this 0 to 5 degree or 0 to 10 degree, we give the masking. So when the satellite is present between this, so it get masked, and it doesn't misrecorded into the data. So then we get the less multipath and as well as less signal loss into our data. But the this limitation of this masking, we sometime when the signal availability is less, there are only 5 6 satellites available in your area. So when you are giving more masking, like 10-degree angle, 10-degree elevation and degree you are giving, so what happens, you are receiving very few satellites into your data, so which you don't want. If you are not able to receive more satellite data, so you cannot constrain your solution, you cannot constrain your parameter. So if you want to constrain, and if you want very fixed solution and very accurate and precise solution, so then you need more number of satellite data into your data. So that's why we have to have this site suitability, and we have to do the some testing also. Site testing we have to do, particularly when we are going to set up the base station. So after this site testing, then only we decide whether we have to set up the station here or not. So this is some information about this multipath. So you can see that how multipath varies for different antenna height. And this is the atmospheric delay. So you can see this atmospheric, so this is called low elevation angle, and this is high elevation angle. So high elevation angle there is no problem, but low elevation angle there is a problem. And this is the zenith delay from the weight and dry component. So you can see this your weight component is not easily modeled, but dry component can be easily modeled through your three measurement: pressure, temperature and humidity. And this is the multipath and water vapor effect in the observations. So you can see for 3 different time period, you can see this, so how it varies. Then unmodeled motion of the station. So here you can see these are the unmodeled motion. So like this earthquake, okay, and then some this local motion. So all this basically cannot be modeled. So these are very transient motion, and happens very few seconds of time, and because of this, your station can be disturbed, and whole data can be basically waste for that day. So you can see when we see this observation in the logarithmic decay and in its exponential decay, so you can clearly see that this north component in this 2 decay, here it is affected, but here it is not affected. But the east component, you can see in the exponential decay has been affected, but here it is not affected. But the advantage in logarithmic and exponential, so when you are looking for vertical fluctuation, so in both the decay you can see there is no problem in the vertical motion. So when there is an earthquake, so you can see the offset, on that day or on that time, you can see clearly the offset. So there are so many earthquake occurred, so we mainly observe in the horizontal component, we don't see in the vertical component, but we can see the fluctuation. So you can see it this sinusoidal motion was going like this, but as the earthquake has been occurred, so due to the motion, and it has this fluctuation has gone up, because of this earthquake phenomena. Then this you can see the groundwater variation. So groundwater variation basically due to this loading and unloading, there is a elastic basically variation. So compression is there and relaxation is there. So this compression and relaxation causes variation, changes in your this it basically change your monument setup, base station, our campaign station, it change. So that's why. And it mainly happens when we are looking for yearly data. So when you see the yearly data, so you will clearly see this groundwater variation effect into your data. So that is called non-tectonic component. So because there are two components when you are setting up the this station. So this tectonic component mainly due to the plate motion, or non-tectonic component due to the hydrological component, atmospheric loading, so tidal loading. So when you are measuring this data along the offshore, along the coast of the this plate, so then you will see that more tidal effect is in your data than this groundwater variation. So these three parameter basically largely affect through the this hydrological variation into your data. And these are the this annual component of vertical loading variation throughout the globe. Then this another unmodeled this motion of the satellite is your as I talked about this solar radiation pressure, unbalanced thrust, outgassing, non-spherical antenna pattern. Okay, so these are some unmodeled. And this reference frame, I already talked about the reference frame, so I will not go again here. So now comes to the some practical aspect. This theoretical part has been over. Now I will talk about the practical aspect. So practical aspect mainly for this gamete data processing. Gamete is freely available, who is associated with any organization teaching, either teaching our R&D. So they can download, they can get the license freely from MIT USA, and then they can start the this uh, processing for the static as well as kinematic motion. So you can see this, you have to do the preparation. So like this, you have to do this. So there are different agency providing this instrument for this GNSS data collection. Leica is there, Trimble is there, Septentrio is there, Astag is there, some more agencies is there, manufacturer who are providing the this antenna and complete instrument. And then you can convert into Rhinex, and Rhinex full form is receiver independent exchange format. So this is the standard format to process the data in any software. So this is how you can do this. So this is the taxi. Taxi is freely available, as well as RU and PKR is also freely available. So when you use this platform, you can get the Rhinex file from the binary file. So they initially provide the binary file where it is having the all the this ephemeris information as well as the observed information from the different constellation. So this is information about the Rhinex format. So how we have to take care with this data. And then this is the Rhinex data format. So here you are getting the header information, that the a priori coordinate, your this marker name, marker number, antenna height, antenna version, antenna model of the antenna, receiver model, receiver type. So all this information is available here. And then what are the observation it has measured, types of observation. So you can see C1, L1, L2, P1, P2, S1, S2, it has measured in this data set, in this Rhinex file. And you can see here is the observations, type of the first observation, time of the first observation, and end of the header. So this is the end of the header. So this is the time, and these are the satellites. Okay, GPS satellites, and this is the data. So the data is basically arranged in this format only. So this is C1, this is L1, this is L2, P1, P2, S1, S2. Like that, this data has been arranged throughout the time. So you can acquire, depending on your requirement, you can acquire every second, our 15-second sampling interval, 30 second, 60 second. So depending on your objective. So if you are looking for a very slow movement, and if continuous movement is there, so you want to monitor it, so you have to do the kinematic measurement. So kinematic measurement can be done in 1 hertz sampling interval. So and if you are doing for this tectonic, so you can collect in 15 second, 30 second, like that. So this two is preferable, 15 second or 30 second for tectonic measurement, tectonic study. And when you are going for this gamete processing, so you have to make so many folders. So like you are doing for this different year data processing, so you have to make folder like this. And then, and suppose this is the, this subsection is showing for this 2013, so it will have this BRDC file where it will keep navigation data. Then here it will keep the orbit file, here it will give you the solution, here it will give you the sp3 file. Okay, Rhinex file from IGC station, from your rover station, base station, all those data will be here in this folder. And this table, here you have to do so many setups basically, like processing setup you have to do, station info you have to update, and then this data, so many data you have to download. So all those things we have to take care into the table. And after the completion, so this is the some schematic diagram. So here this is the flow chart, how you can do this data processing in this format. And after the after getting this h file of from gamete processing, you can generate the time series as well as velocity with the help of this command, glret and globe-k. So these two commands give you this time series and velocity using the Kalman filter. And this is the another preparation when you are going for this data processing. So time is limited, so I will quickly go to the next slide. So this is the basically gamete processing, and this sh underscore setup is to create the tables, and these tables will be having all this data. And this Rhinex, as I already told you, we have to keep in the Rhinex folder. And then we have to use this command to update the your station info, like header information, antenna information, receiver antenna height. Okay, all this information we have to update through this command. And this is for getting the a priori coordinate from the Rhinex data. And then once we complete all this once we complete all this preparation, then we use this command to run the gamete. And after the processing, we get this loosely constant solution. And here you can see it is having 10 to the power 3 in the pre-feed. This is the error actually. And after running this double difference and post processing, you can see this 10 to the power 3 has been gone. And now the data is in post feed, and it is having in subdecimal range error. So you can see this constant free and constant fix, this is loose free and loose fix. So this is the four different this pre-feed and post-feed we get after the gamete processing. And this is the your error modeling and error visualization, that how much error is associated with the data after the completion of the processing. So you can see this low elevation angle, it is having little bit more error, but when you are going for this high elevation angle, like this is 90 degree, so you can see error is reducing, it is constraining between these two range. So this is the uniqueness of this gamete processing, which basically after so many covariance matrix, it basically creates the covariance matrix for this error estimation, and then you can visualize how much error is associated with the data. And when you want this kinematic GPS data processing, so there is a one module, track module is there. So when you use this track module, so you can monitor the car, aircraft. So like if there is any uh, co-seismic variation is there, like any earthquake has occurred, any volcanism has been taken place, any glacier mass is moving, avalanche is about to take place, our land subsidence is about to occur. So all this motion can be monitored with the help of kinematic measurements, and where you have to have 1 hertz sampling interval, then only this kinematic measurement is possible. And if it is moving slowly, so then 15 second 30 second is okay. But when you are looking for this co-seismic earthquake variation, so then you have to have 1 second sampling interval only. So these are some information about the this track module. And after this track data processing for these stations, so you can see this amplitude and the offset at this station due to this San Simon earthquake. So these are the surface wave basically. It doesn't measure the P wave and S wave. It measures the S surface wave. And you can use this data to estimate the your this magnitude, surface wave magnitude. You can with the so it is very very beneficial. So if there is a mega thrust earthquake like 9.5, and sometime our seismometer gets saturated due to this very intense earthquake, so this GPS can be helpful to acquire or to means measure all this data, and then you can estimate this magnitude with the help of various station. So you can see this earthquake signal has been recorded in the GPS station as well, because normally we believe that this will record only in the your seismometer, but it is recording into the GPS station also. And it is only possible when the station is very close to your epicenter, and this some ground movement is optimum ground movement is there. So it is not that if there is a less than 5 magnitude, it will also get recorded in the GPS data. It is not always possible. So optimum movement should be there, then only this recording is possible into horizontal as well as in vertical component. These are some quiz. You can see this quiz, and later on you can go and solve this. So time is very limited. So this is the course network, and here you can see this 600 hour so operational right now. So this green is showing basically the operational, continuously operating reference station, and installed by Survey of India and monitoring by Survey of India, and all the data services providing in real time by the Survey of India. So you can use this data for your the region, and you can do some quality work for different applications like groundwater study, land subsidence study, tectonic study, some different kind of monitoring, our active fault mapping, active fault monitoring study. So various study you can and earthquake precursor measurement study. So various study you can now, and you can carry on with the help of this data, because it is not only restricted to geology, our Simthi, because a physicist also who is working in the atmosphere, lower atmosphere, upper atmosphere, they are also looking for this navigational signal. So Survey of India is giving this government organization free of cost, and you can approach to them. Now some case study. So you can see that this is the velocity, and depicting the this plate motion, our side motion, and this is fixed with respect to Eurasia. So that's why you are seeing more velocity in Himalaya and less velocity in Eurasia, China. So that's why. But here, when we get this less velocity, and if the region falls under the tectonic area, so then we can say that it's a serious matter with respect to your seismic hazard study. So because the region is locked, and if there is no seismicity, so it can produce the big earthquake or mega earthquake in near future. So here one thing is very important. You can notice that this motion is like this. So it is having clockwise motion. So we believe that this Eurasian plate is coming toward us, and it is having clockwise motion. So and our Indian plate is having anti-clockwise motion, and it is already proved by many various researchers. And here these all our seismic hazard assessment has been carried out with the help of GPS and SAR data, and this research has been carried out by Bilham et al. In 2019. So you can see that the patches, these are the locked region actually in the Himalaya, and how much potential is, you can see here. These are the potentiality of the region, and this much sleep deficit is there. So you can see that in starting from northwest to northeast, and very recent earthquake Nepal 2015 occurred in Gorkha region, and these two earthquake in Uttarakhand 1991 and 1999 occurred. The magnitude was 6.1 and 6.7. So which has released some part of the energy stored here, but still there is a huge elastic energy stored in this region. And you can see from this qualitative way of this showing this energy stored in this region. So this is the interseismic phase, and it is after this occurrences of the two earthquake, it has little bit means modulated this strain accumulation, means, and then again it is going in the similar manner. And we believe that in near future, because we have also estimated this sleep deficit, and with the help of this GPS data only, and it is coming around 4 meter. So if you estimate the moment magnitude with the help of this fault parameter, which we got through the modeling Okada, this chi-square uncertainty modeling we got, and it is coming around 7.8 or 8 magnitude can be occur in near future in this region. And this is installed by us, IIRS, our ISRO, and there are some campaign station as well as course station. So of course we can see it is mainly highlighted in red and yellow color, and this blue is representing the campaign station. So these are some outputs. So this is the India fixed velocity, you can see that, and this is the ITRF velocity. So you can see this is the IGP, this is Shivalik, and this is the higher Himalaya. So when we see that this plate velocity with respect to ITRF is nothing but it's giving the velocity from the center of the earth. So this is called geocentric we estimate the geocentric coordinate, and this is the resultant motion actually. This is the resultant motion, absolute motion, and because of this plate motion and through melted convection and other geodynamic process. So here the velocity is reduced in ITRF, but here you can see more velocity. So when we get the more velocity and here we are getting the less velocity, so it depicts that this is under more tectonism, more tectonic deformation is going on here, and less tectonic deformation is going on here, and the main region is, this region is locked. So this is the your different strain budget estimation. So like the here strain dilatation is there, your rotation is there. So like anti-clockwise motion, clockwise motion we have observed over this region, as well as how much shearing is going on in this region, because this is not only having the translation motion, this is having the rotational motion also. So we have estimated all these strain parameter in this region through this local measurement, and this is the regional measurement of strain. So this is, here you can see the compression, that how the compression is going and what is the orientation of the compression, how the plate is basically colliding to each other, and where the more compression is taking place. So all those estimation we can do with the help of GNSS. So the GNSS basically revolutionized. It has revolutionized this tectonic geodesy, and because of this revolution, we are able to study this movement efficiently and very precisely. And the work has been published by many researchers in Science, Nature, for this Himalayan region since 1997 to present. And this is the modeling result. So, and you can see there's model data from GPS, and this MT data is correlating to each other and clearly depicting that there is a linkage between this empty result and your GPS observations. And after this constraining all this study, we can say that this region is under a huge intense seismic potential and can have this mega thrust earthquake in near future. And we have done some hydrological study also through GRACE data and GPS data. So you can see this correlation coefficient between your GRACE and GPS. So these are the three components. This is north, east, and vertical. So you can see there is a linkage that this hydrological component is influencing this your north component and vertical component more than the east component, because east is the strike direction component, and it is having less influence due to the hydrological loading. And you can see this consequence of this hydrological loading. So there is a microseismicity in the region. So you can see the more, this is the percentage of the microseismicity. So more earthquake occur in the post monsoon, post to pre monsoon, than the during the monsoon. Co monsoon there is a very less earthquake, because then the region is under extension, and when this hydrological loading has gone, then the region again under compression. So because of these two phenomena, there is a variation in the seismicity. And this is the schematic diagram and some model to explain this your elastic compaction and compression and relaxation. And we have also basically we are also studying this earthquake precursor through TEC measurement. So these are some findings from TEC measurement. So there was an earthquake, Mirpur earthquake. So we have captured this earthquake into our GNSS data placed in northwest Himalaya, and this is the signal. You can see the variation in such this small region. There is a variation in the tech variation. This is the diurnal variation actually. This is the diurnal variation, and you can see that this diurnal variation is mainly maybe affected by this basically pre-seismic activity and pre-seismic seismogenic activity. So this pre-seismic, because this is phenomena we have observed on 10th, and this we have observed on 17th, and then earthquake has been occurred on 24th September. So this anomaly basically gives an clue that there could be a medium earthquake or mega thrust earthquake. So and when we get this clue, so then we estimate the anomaly. So we have developed the statistical method to get the upper positive anomaly and negative anomaly. So this positive and negative anomaly depicts that there could be an earthquake from the neighboring region, and this method works for more than 5 magnitude, and if it falls under the earthquake preparation zone, then only we can detect this earthquake precursor. And also the condition is there should not be any solar and geomagnetic activity, because this negative anomaly can be created by this solar and geomagnetic activity as well, because earlier we were thinking that this negative anomaly can be produced only by the seismogenic activity, but we have also detected this negative anomaly, huge variation in the negative anomaly through this solar and geomagnetic activity over Himalayan region. So we are preparing this manuscript, and we will submit soon into the journal to give this information also. that this negative anomaly cannot only happen due to seismogenic activity, but can happen because of solar and geomagnetic activity as well. And with the help of this tech variation, we can get the possible epicenter information also. So you can see here it is giving 36 kilometer, and here we have 28 kilometer. So you can see there is a very less difference between the actual epicenter and predicted epicenter. So this 8 kilometer difference is nothing actually. If we are able to get this information 10 days or 15 days before an earthquake, so there is no bad thing. But the only thing, how we can enhance our confidence, how we can enhance our confidence that this anomaly is going to cause an earthquake. So we have to basically have more this data, then only we can enhance our confidence, so that we cannot give the false alarm. And earlier I have shown you the this time series analysis, and this is the 2D analysis. So 2D this time series can be done with the help of our data, our ground data, and this 2D data is freely available through your gym data, and it is provided by University of Bern, Switzerland. And you can clearly see that this time series data and 2D data has observed the anomaly. This is again the negative anomaly before this earthquake, and you can see for the same time there was no anomaly, though there was no anomaly. But for on this day, on 16th September, there is a huge anomaly, and on 24th the earthquake has been occurred, and this was the epicenter actually. So you can see just close to epicenter the anomaly has been created, negative anomaly. So, and this is another example of this advanced GNSS data processing for this Josimat region, that how the subsidence took place in the Josimat region. And this you can clearly see the non-linear motion, because normally we expect linear motion from the base station, that it will go linearly, but this non-linear motion clearly depicts that there is a episodic movement took place in the Josimat region, and where the this movement was very high at this place. But when we see in the Ravigram, which is very close to your this station, so there we can see the less motion. And this is campaign station we are monitoring since 2015, but we have observed less this displacement as well as velocity at this place. So this is the documentation of the this different parameter, like average displacement, total displacement for this Josimat station, which is provided by, which is monitor installed by Survey of India. And this campaign station is set up by us, and sorry, acquired by us, and this station is provided by Survey of India only benchmark. So you can now and these are some references which you can use it to get the this fundamental of GNSS, to understand the more to get the more knowledge about the advanced GNSS data processing. And if you want manual of gamut, globe K, and GMT, you can get it from this link, and where you can start this work for your different application. So thank you very much.